Hello, this is Kandai Watanabe, a PhD student at the University of Colorado Boulder. In this video, I will present our work on probabilistic specification learning for planning with safety constraints. So robots nowadays work in various domains from deep space/sea exploration to human shared assembly line. As they advance into these fields, they are expected to perform challenging tasks whose specifications are often difficult, if not impossible, to accurately define. But in these scenarios, it could be extremely easier for us to just show the demonstrations at that spot. So imagine a task where an autonomous underwater vehicle has to visit new locations. So for example, a school of fish and a shipwreck in any order. It might be easy for a non-expert to just show demonstrations instead of programming the task. So our goal here is to teach robot a task by showing demonstrations so that anyone like tour guide can easily define a new task by themselves. At the same time, there are always key safe properties we want the robot to maintain. And we never want the robot to go into, for example, coral reefs and get stuck there. We always want to ensure safety while learning the specifications of a task. So this type of work is called learning from demonstrations, and most of the work focuses on learning policy or work. These methods suffer from learning no mark given task. For example, to visit both shipwreck and fish as in the figures, robot has to remember which state it has visited in the past in order to visit the other goal. They also have difficulties transferring to different environments in robots because they depend on the environmental states, like what actions to take at a specific locations represented as arrows on the left figure, or how much reward you get at a specific location. Instead, we tackle this problem by learning specifications of a task in a formal language. So the formula of this task can be described as eventually shipwreck and eventually fish. Previous approaches learn a formula by inferring the most likely formula from a set of all possible formulas, but it requires prior knowledge, slow due to sampling, and suffer from state explosion problem when converting to automaton below for planning. Instead, our idea is to learn this automaton directly from demonstrations. So specifically, we learn a probabilistic deterministic finite automaton (PDFA), which can encode non-mark given task and demonstrate its references as a probability distribution. A PDFA is defined as a tuple where Q is a set of nodes Q0, Q1, Q2, Q3. A sigma is a set of symbols, for example, where we define symbol as a part set of atomic propositions. But in this example, a symbol is defined as a single atomic proposition like shipwreck and fish. And it starts at the initial state, Q0, transitions to the next state according to the deterministic transition function delta by observing a symbol sigma, and ends at the terminating node defined by F with the terminating probability of Fp. And each transition is associated with a symbol with the preference probability, which represents which action is most likely to be taken. And we can define a demonstration as a finite sequence of symbols. In other words, we call it a trace. So a trace could be, for example, empty, shipwreck, empty, fish, and accepted by the terminating node. And we can define a probability of a trace, which is a multiplication of the transition probabilities and the terminating probability. So a trace, the probability of this trace could be 0.5 times 0.4 times 0.5 times 0.5 times 1.0, which is 0.05. And if the probability is larger than 0, we say that the trace is valid or accepting by this PDFA. And a set of all accepted traces are called a language of automaton. So given a set of demonstrations, we want to learn a task as a PDFA such that all demonstrations are accepted by this PDFA while ensuring safety. So in this work, we express the safety constraints using safe linear temporal logic, which is a fragment of LTL. LTL reasons about how properties of a system change over time, and it can be defined recursively as the following, where P is an atomic proposition, and not and or are the operators, and X and G are temporal operators. So for example, never going to coral reefs can be expressed as globally not coral. And we can always translate this safe LTL to safety DFA. And in our work, we assume that the safety is given by the demonstrator in a form of safe LTL. So we divide this problem into two problems. First is the PDFA inference problem, giving a set of demonstrations and a safety specification. We want to learn the task with demonstrator's preferences as a PDFA, such that safety is never violated. And once we learn the PDFA and giving a robot that can be abstracted to a deterministic transition system, a DTS, we want to compute a plan for the robot that generates the most preferred behavior that satisfies the learned task. And we will show that we can apply our method to various robots in different environments. So first, I will explain how an automaton can be learned. Automaton learning is widely explored in grammatical inference community, and this is the first research that I know of bringing automaton learning into robotics. So to infer an automaton, we employ off-the-shelf grammatical inference algorithm called EDSM algorithm. At a high level, it learns the structure and the probability distribution of a PDFA. In more specific, we map all traces to a tree and call initial node red, its children blue, and compare the red and blue node if they're similar based on the similarity measure, and merge if they're similar. We continue this process until we cannot merge anymore. However, since this is a heuristic algorithm, this may induce unsafe behaviors. To this end, we've introduced a method to embed safety constraints during learning so that the learning outcome will never violate the safety constraints. So given the safety LTL formula, we first translate it to a DFA, and then by running the traces of the tree on this automaton, we label each state of the tree with the state of the safety DFA. We only allow merges between two nodes that have same safety DFA states. This ensures that the safety specification is never violated, and this is a simple trick but turns out to be very effective. The main idea behind this algorithm is called a simulation relation. A simulation relation means that there's a relationship between the states of two automata A and B. There are three conditions for a relation to be a simulation relation. And let's use this example to illustrate the conditions. So if F0 and T0 are in relation, if F0 has a transition under A to S2, then T0 has to have a successor under A, which is, in this case, it's T1. So S2 and T1 have to also be in a relation. And the other two conditions are simple. If F0 is an initial state, T0 has to be an initial state. Finally, if F0 is an acceptant, then T0 has to be an accepting as well. In this example, S3 is accepting, and it's in relation with T0, and T0 is also accepting. In our algorithm, we maintain this simulation relation between the intermediate tree A and safety DFA B by only allowing merges between the two nodes with the same safety states. So that all transitions in the intermediate tree will exist in the same in the safety DFA. If there exists a simulation relation between two automata A and B, from the well-known theorem, we say that B can simulate A. In other words, the language of A is a subset of a language of B. What it means is that all traces in A, in our case, the intermediate tree A, can be run in this safety DFA B. This ensures that we never violate safety specifications. So once it's learned, we want to apply the learned specifications to different environments. Here we present our sympathetic planning algorithm for computing a plan that completes the learned task in the environment we are interested in, while maximizing for the demonstrator's preferences. So in order to achieve this goal, we use an established method known in formal synthesis that is to construct a product between a learned PDFA and a transition system. So first we have a PDFA that we learned and a robot in an environment that we are interested in. Next, we abstract the motion of the robot in this environment into a deterministic transition system, DTS, and construct a product automaton between these two graphs. The product automaton captures all the ways the robot can achieve the task. And in the product, we inherit the probabilities from the PDFA, but here they are no longer true probability distributions. We're interested in computing a path to an acceptance state on this product that once mapped back to the PDFA, it will have the highest possible probability given the robot's constraints. This could be a cumbersome process, but we use a trick to reduce it to a simpler problem. So instead of looking at the product of the transition probabilities, we take the negative log of the probabilities so that we turn the product into summation. And this now becomes a simple search problem for the shortest path on a graph. So we can simply run a Dijkstra's algorithm on this graph. A plan on the product can always be mapped to the original DTS so that it's always going to be a valid plan with the highest preferences. And now I will present examples and applications of our algorithm. In the first case study, we showed how non-Markov tasks can be learned using our method. So first, let us assume we have a latent task of go to both fish and shipwreck in any order with the preference of visiting shipwreck first and always avoid coral reefs. The latent task can be converted to DFA as follows. It is preferred to visit shipwreck first and then fish. We sampled 1,000 traces and ran our method and got this automaton on the right. We can observe that the structure is exactly the same and the probability looks very similar to the original PDFA. Then, using the learned PDFA, we synthesize a plan on the original environment. The resulting path takes the preference into account and visits the shipwreck first and then the fish. We modify the environment so that the fish blocks the shipwreck. Notice that the path has changed to visit the fish first and then the shipwreck. It computes the most preferred plan, which is the correct behavior. In the next case study, we will learn the specification of a task from a small number of the samples presented in the following paper, and we compare our method against their work. So we now have a new scenario where the latent task is to visit a charging station if not wet. If wet, the robot has to dry up the carpets. And we learn from a small number of demonstrations and obtain two different outputs depending on the hyperparameter alpha, which is a measure of how aggressive we allow merges in the EDSM algorithm. So higher the alpha, the smaller the automaton. And noting the left PDFA, charging station denoted by G must always be observed to reach the final state. And this shows that the task of reaching the charging station is learned correctly. And next, on the right-hand side of Q0, W is observed to visit the island on the bottom, and the only way to exit this island is by observing C, which is carpet. So the left automaton learned all the specifications of the task correctly. However, the right automaton only learned to visit the green charging station denoted by G and pruned all other information. And if you use this for synthesizing a controller on a different environment, so you can compute a plan that induces unsafe behavior that goes into the water. But if we embed safety specification, our method always guarantees a safe plan regardless of any hyperparameter values or any number of demonstrations. In conclusion, we propose a new approach to task learning and planning with safety guarantees. In addition, our method only took 0.1 second to learn from 5 samples, whereas the previous method took 95 seconds. Next, from the same automaton, we sample a large number of samples and learn more general tasks given the safety specification. And we transferred to other environments. So even if you modify the transition system so that robot moves diagonally, it can complete the plan. And this is same for the rotate and directional robots. It can complete the plan while never violating safety. We also applied our method to different environments and to a manipulator example to show that our method is not limited to mobile robots. But due to the time constraints, we included them in our YouTube video. So in conclusion, we propose a new approach to specification learning and planning with safety guarantees, embedded preferences, and compatibility with various robotic models and environments. Applications include model delivery so that robot can learn from demonstrations, and where to visit, and in which order to visit. Thank you.